Today I will introduce Olbedo, a large-scale aerial dataset for outdoor albedo and shading decomposition. The key message is simple. If we want photorealistic digital twins that can be relit and edited, we need to separate material from illumination. Olbedo provides this supervision for real UAV imagery. The bottleneck starts in ordinary photogrammetry. UAV images already contain cast shadows, sky shading, and view-dependent lighting. When these images are baked into a three-dimensional model, the shadows become part of the surface texture. If we later place the model into a simulator, the renderer adds new lighting on top of the old one. This creates double shadows and unrealistic appearance, even when the geometry is accurate. To address this, we use intrinsic image decomposition. A radiance image is factorized into albedo, or reflectance, multiplied by shading. For outdoor aerial scenes, shading is not a single term. It includes direct sun shading, sky illumination, and weaker indirect light. The desired albedo is the illumination-invariant material layer that should remain consistent across time, weather, and viewpoint. The key observation is that multi-view aerial capture gives us geometric context. Lit and shadowed observations, together with reconstructed geometry, provide constraints for estimating the sun-to-sky lighting ratio. This lets us remove lighting effects from source images even when the scene is captured during a single flight, rather than under many carefully controlled illumination conditions. Olbedo turns this idea into a dataset. It contains 5,664 UAV images, collected across 4 landscape types and multiple years. Each view is paired with dense albedo and shading labels. More importantly, these labels are multi-view consistent, so they can support not only single image prediction, but also downstream three-dimensional workflows, such as retexturing and relighting. Our pipeline starts from raw UAV captures. We first recover accurate camera poses and scene geometry. Then we estimate outdoor illumination using the sun position and sky observations. Finally, an inverse rendering refinement step produces pseudo-ground truth albedo and shading. The pipeline is designed to be practical for real outdoor data, where fully controlled ground truth is extremely difficult to acquire. Along with albedo and shading, Olbedo releases several auxiliary annotations. For each view, we provide RGB images, metric depth, surface normals, sun shading, sky shading, and illumination information. These outputs make the dataset useful for training intrinsic decomposition models, but also for future multitask learning, geometry-aware scene understanding, and physically based outdoor rendering. Because this is real outdoor data, our labels are pseudo-ground truth, not perfect laboratory measurements. However, the important question is whether they are useful supervision. We use them to fine-tune pre-trained albedo prediction models. The learned model can then take a single aerial image and predict cleaner albedo without requiring multi-view geometry at test time. The results show that Olbedo teaches existing IID models outdoor lighting. After fine-tuning, several pre-trained intrinsic decomposition models achieve clear improvements on outdoor benchmarks. Visually, the predictions suppress baked shadows, reduce shading leakage, and preserve details on roads, roofs, vehicles, and facades. The error maps also become more blue, indicating lower albedo error after Olbedo fine-tuning. Once albedo is available, it enables a family of illumination-aware three-dimensional workflows. First, texture quality improves, because lighting artifacts are reduced before reconstruction or rendering. Second, material editing becomes more realistic, because we edit reflectance while preserving shading. Third, change analysis becomes more robust, because albedo suppresses false positives caused by moving shadows, weather differences, or illumination changes. Here is one example in relighting and retexturing. A model textured with the original image keeps the old shadows from capture time. In contrast, a model textured with our albedo is closer to a true material map. When it is rendered under a new sky or sun direction, the lighting is generated by the renderer, rather than being baked twice into the texture. To summarize, Olbedo provides real aerial supervision for outdoor intrinsic decomposition. It improves the generalization of existing albedo prediction models to aerial scenes, and it supports downstream applications such as relighting, retexturing, material editing, segmentation, and change analysis. We hope Olbedo helps move aerial digital twins toward illumination-invariant, editable, and physically meaningful representations.